There are so many mysteries lurking out there in space that scientists are working to unravel. However, to get a better grip on these mysteries, scientists are daringly attempting to recreate them in the lab with the help of the latest technologies, like how they created a wormhole using Google's AI computer. However, they quickly shut down the experiment. How scientists do science has come a long way, especially with the help of modern-day technologies. Earlier scientists would be surprised or even scared by how much their successors have built on their initial discoveries. Take as an example wormholes. A wormhole is a special solution to Einstein's general theory of relativity equations that connects two distant points in space or time via a tunnel. The length of this tunnel should ideally be less than the distance between those 2 points, making the wormhole a kind of shortcut. Wormholes were only hypothetical despite being common in science fiction and capturing the popular imagination. However, they are legitimate general relativity solutions, but scientists never discovered a way to keep a stable wormhole in the real universe. Until Google's quantum computer came along. But where do wormholes come from? Albert Einstein and Nathan Rosen discovered the simplest possible wormhole solution in 1935, which is why wormholes are sometimes referred to as Einstein-Rosen bridges. Einstein and Rosen began with a mathematical solution to the problem of a black hole, which consists of a singularity, a point of infinite density, and an event horizon, a region surrounding that singularity beyond which nothing can escape. They discovered that they could extend this solution to include the polar opposite of black holes, white holes. These hypothetical white holes, like black holes, have a singularity, but they operate in reverse. Nothing can enter the white hole's event horizon, and any material inside the white hole is ejected immediately. Einstein and Rosen discovered that every black hole is theoretically paired with a white hole, but because the two holes would be in different locations in space, a tunnel, a wormhole, would connect them. So what do wormholes look like? A wormhole would appear very strange if you encounter one. The entrance would be a sphere similar to a planet's surface. If you looked closely, you would notice light coming in from the other side. The wormhole tunnel could be any length, and as you traveled down it, you would see distorted views of the region of the universe from which you came and the region to which you were traveling. If you are fascinated with time travel, a wormhole can also function as a time machine. Moving clocks must run slowly due to special relativity. In other words, someone moving at near light speed would not advance into their own future as quickly as someone standing still. If scientists could create a wormhole, the two ends would initially be time synchronized. However, if one end were accelerated to nearly the speed of light, it would begin to lag behind the other end. The two entrances could then be combined, but one of them would be in the past of the other. To go back in time, simply walk through one end. You'd find yourself in your own past when you emerge from the wormhole. However, what do you get when you combine quantum computing and wormholes? The world has changed due to quantum computing. It has revolutionized communications and artificial intelligence as well as transformed medicine. And Google has claimed quantum supremacy, which means that a quantum computer has outperformed a traditional one. But what exactly is quantum computing and how does it function? Bits are used in standard computer chips. These are similar to tiny switches that can be in the off, represented by a 0, or on, represented by a 1 position. Every app you use, every website you visit, and every photograph you take is made up of millions of these bits in some combination of ones and zeros. Quantum computers use qubits instead of bits. The difference is that qubits can be both on and off at the same time, or somewhere on a spectrum between the two, rather than just being on or off. Look at a coin, for example. If you flip it, it can be either heads or tails. If you spin it, it has a chance of landing on heads and a chance of landing on tails. It could be either until you measure it by stopping the coin. Superposition, like a spinning coin, is one of the things that makes quantum computers so powerful. A qubit allows for uncertainty. So for example, if you ask a normal computer to find its way out of a maze, it will try each branch individually, ruling them all out until it finds the right one. A quantum computer can traverse the maze at the same time. Entanglement is another property that qubits possess. Normally, if you flip two coins, the outcome of one has no bearing on the outcome of the other. they're independent. Entanglement occurs when two particles are linked together despite their physical separation. If one comes up heads, the other will as well. Let's explore the relationship between wormholes and entanglement next. Physicists Leonard Susskind of Stanford University and Juan Maldacena of Princeton's Institute for Advanced Study were interested in how two black holes entangle to one another. Entanglement is thought to occur between tiny particles rather than massive cosmic objects. However, if two black holes were entangled and then separated, the physicists reasoned the result would be a wormhole connecting them. This made Susskind and Maldacena propose a link between wormholes and entanglement. Since then, independent teams of researchers have supported the concept. They demonstrate theoretically that entangled quarks are linked by a wormhole within a simplified version of reality. According to this model, the wormhole exists in our 4D world, 3 dimensions of space and 1 dimension of time, but the quarks are only entangled in a flattened 3D simulation of reality. This is analogous to using a 2-dimensional hologram to represent a 3-dimensional object. So in other words, wormholes exist wherever there is entanglement. The pair went so far as to define the two as ER equals EPR, where ER refers to an Einstein-Rosen bridge or wormhole, and EPR, short for Einstein-Podolsky-Rosen, is another term for entanglement. Daniel Jefferies and Ping Gao of Harvard University and Aaron Wall of Stanford University have also shown that wormholes can exist. Finding a way to build a wormhole through which light could travel was a significant step forward in the quest to develop a theory of quantum gravity. The true significance of this research lies in its application to the black hole information problem and the links between gravity and quantum mechanics. The new theory was inspired by Jefferies' thoughts on two black holes that were quantum entangled, as formulated in Maldacena and Susskind's ER equals EPR correspondence. Although this implies that the direct connection between the black holes is shorter than the wormhole connection, and thus wormhole travel is not a shortcut, the theory provides new insights into quantum mechanics. Jefferies' theory is based on a setup devised by Einstein and Rosen which consists of a connection between two black holes. The wormhole was a special case in which information could be extracted from a black hole because it was traversable. It provides a causal probe of regions that would otherwise be hidden behind a horizon, as well as a window into the experience of an observer inside a space-time that is visible from the outside. To date, the requirement for negative energy, which appeared to be inconsistent with quantum gravity, has been a major stumbling block in developing traversable wormholes. Jefferies, on the other hand, has overcome this by employing quantum field theory tools to calculate quantum effects similar to the Casimir effect. And if you wonder what negative energy is, here's what it's about. The gravitational potential energy that holds two pieces of matter together must be negative because it takes positive energy to separate them. Given a roughly uniform universe, the total negative gravitational energy in it would exactly cancel out the total positive energy represented by matter. As a result, the universe as a whole has no total energy. Scientists, however, have succeeded for the first time in developing a wormhole in the laboratory. According to the scientists behind the work, it constitutes a step toward a larger program of testing quantum gravity physics using a quantum computer. The current work investigates the wormhole quantum teleportation equivalence. The Caltech-led team conducted the first experiments to investigate the idea that information traveling from one point in space to another can be described in either wormholes or quantum entanglement. In 2015, Alexei Kitaev, the Ronald and Maxine Lind Professor of Theoretical Physics and Mathematics at Caltech, demonstrated that a simple quantum system could exhibit the same duality later described by Gao, Jefferies, and Wall, such that the model's quantum dynamics are equivalent to quantum gravity effects. This Sachdev-Yek-Kitaev or SYK model led researchers to suggest that some theoretical wormhole ideas could be studied more deeply by conducting experiments on quantum processes. This type of experiment was carried out for the first time in the new study by a team of physicists. They used a baby SYK-like model that was prepared to preserve gravitational properties, and they observed the wormhole dynamics on a Google quantum device, the Sycamore quantum processor. To do so, the team had to first simplify the SYK model, which they accomplished using machine learning tools on standard computers. They used learning techniques to find and prepare a simple SYK-like quantum system that could be encoded in current quantum architectures while retaining gravitational properties. In other words, they simplified the microscopic description of the SYK quantum system and studied the resulting effective model that they discovered on the quantum processor. It was fascinating and surprising how the optimization of one model characteristic preserved the other metrics. They intend to conduct additional tests in order to gain a better understanding of the model itself. The researchers performed the experiment by inserting a qubit into one of their SYK-like systems and observing the information emerge from the other system. The information was transferred from one quantum system to another via quantum teleportation, or in gravity's complementary language, through the traversable wormhole. They performed a type of quantum teleportation equivalent to a traversable wormhole. To do so, they had to simplify the quantum system to the simplest example that preserved gravitational properties, which they then implemented on Google's Sycamore quantum processor. It took a long time to arrive at the results, and they were surprised by the outcome. The gravitational perspective offered a simple way to understand an otherwise mysterious many-particle quantum phenomenon. But perhaps what was most interesting about the new Google experiment was that they were able to make the system simple enough to simulate an existing quantum machine using machine learning while retaining a reasonable caricature of what the gravitational picture predicted. The physicists reported wormhole behavior expected from both gravity and quantum physics perspectives in their study. While quantum information can be transmitted or teleported in a variety of ways, the experimental process was shown to be, at least in some ways, equivalent to what might happen if information traveled through a wormhole. To accomplish this, the team attempted to prop open the wormhole with pulses of either negative repulsive energy or positive energy. They observed key signatures of a traversable wormhole only when the equivalent of negative energy was applied, which is expected of wormholes. The high fidelity of the quantum processor used was critical. If the error rates had been increased by 50%, the signal would have been completely obscured. But if they were half the size, the signal would have been 10 times higher. Let's hear what you think about wormholes and quantum computers in the comments section below.